Alright guys, so I did record the stuff in class the other day. It just wasn't the greatest of recordings, so I'm just going to quickly go through these videos here with you now. So starting off with example C here, and that we're asked to integrate the function of tan of 2x plus pi on 3 dx in between pi on 6 and pi on 2. So having a look at that, and when we look at our reference sheet, we know nothing about tan on our reference sheet. We know something about sine, we know something about cosine, and we know something about sec squared, but we know nothing about tan. So what can we do to tan? Well, previously, what we've done is when what we've been trying to integrate hasn't been in the greatest of forms for us, we've forced it to look like something else. So having a look, what do we know about tan? Well, I know that tan theta is just sine over cosine. I know that about tan. So what we can say here is that, this integral is equal to the integral between pi on 2 and pi on 6, and I'm just going to express tan in terms of sine and cosine. So sine of 2x plus pi over 3 all over cosine of 2x plus pi over 3 with respect to my small change in x. Now, I know something about sine and I know something about cosine, so that is great for me. However, what you might notice now is we've got this ugly fraction, and we don't like fractions. And when we look back at derivatives, we had a rule for finding the derivative of a fraction, but we actually don't have any rules for finding the integral of a fraction. So that's annoying. But if we look on our reference sheet, we actually have something to do with fractions. We can see that on our integral sheet, we know that the integral of something, a fraction in the form where, well, you can't see that, where the numerator is the derivative of the denominator. We know that is just ln, the absolute value. How about we move this down and across a little bit? Ln, the absolute value of whatever the function was, plus our constant of integration. So, maybe that applies here in this situation. Well, if we have a look at this, I've got cosine in the denominator. The derivative of cosine is negative sine. I've almost got negative sine up there. So we know our trick. We can force it to look like that. So if I was to go like this, pi on 2 and pi on 6 of sine, give myself a bit of room, 2x plus pi on 3 over cosine of 2x plus pi on 3 with respect to x. Well, we know we can make that look like what we need it to do. We know that the derivative of cosine is negative sine. So I need to make it a negative in front of the integral, inside the integral, sorry. So remember, outside, I need to undo that change as well. And it needs to be the derivative of the bottom. Now remember, the derivative of cos is negative sine, but remember, we've got to look at what's going on inside as well. The derivative of cos of 2x is negative 2 sine. This 2 has to come out front. So what we need to do is we need to put a negative 2 into our equation, and ideally it goes there next to sine. So to undo putting 2 in, I've got to multiply by negative a half on the outside. Cool. So we've taken something not very nice like tan, used what we knew about tan, and then looked at our integral sheet and said, why we don't have anything for a fraction when I recognize I've got a fraction where the numerator is the derivative of the denominator. Well, I can use logs and the logs of the natural number to get me there. So where we are now is that this integral here, it is just equal to negative a half outside of ln of cos the absolute value of 2x plus pi on 3 between pi on 2 and pi on 6. So now that's great. Let's go through and evaluate this. So it is going to equal negative a half outside of ln the absolute value of cos of 2 pi over 2, because 2 times pi over 2 is 2 pi over 2, which, funny enough, just becomes pi. Alright, so 2 pi over 2, which is pi. So I'm going to change that now to pi. Actually, over here, if I have 2x, 2 lots of pi on 2 equals 2 pi on 2, which equals pi. I'm just going to do, you can't see that, off to the side here. And 2 lots of pi on 6 equals 2 pi on 6, which equals pi over 3. Just going to calculate them off to the side there, and then use them when I need to evaluate them back in. So pi on 2, which is just simplified to pi, plus pi over 3, absolute value of that. I'm going to chuck this in brackets because it's minus ln the absolute value of cosine of, this is where I need to substitute pi on 6 in, and pi on 6, when I times it by 2, we know simplifies to pi over 3, so cosine of pi over 3 plus pi over 3, absolute value of that. Cool. So moving along, let's simplify this a bit. Negative a half of the absolute value of ln of cos of, well, this needs to become 3 pi on 3 if I want to add them together. So we are left with 3 pi on 3 plus pi on 3 is 4 pi on 3. Minus ln of absolute value of cos pi on 3 plus pi on 3. Well, that gets us to 2 pi over 3. Alright, so now we need to think over here on the side, what do I know about 4 pi over 3? Well, 4 pi over 3, if I'm just thinking here for a moment, 4 pi over 3, if I come back here, what I've actually got written in here, if we just pause for a second, was pi plus pi over 3. Right, pi plus pi over 3. Now, pi plus pi over 3, pi, we know, is 180 degrees. So I've got 180 degrees plus some extra little bit. So 4 pi over 3 was pi plus pi over 3. And if we remember, quadrant 3 was 180 plus theta. So 4 pi on 3 exists in the third quadrant. And in the third quadrant, it behaves like pi over 3. And what do we know about pi over 3? Pi over 3 is 60 degrees. So the related angle, let's do that again. The related angle is, it's happening at 60 degrees or pi over 3. And what do we know about 60 degrees and pi over 3? Well, 60 degrees and pi over 3, that is pi over 3, 60 degrees. Exact ratios, looking at my triangle. So thinking about that triangle, I have 60 degrees down here, that's 2, that's 1, and that's root 3 in that triangle there. Cosine is adjacent over hypotenuse. So pi over 3 is half. Cosine of pi over 3 is half, because we're in the third quadrant. That's negative half. That was a bit crazy. I think I talked a bit fast through that, so hopefully you followed that. But I know what I've got here is my first bracket is ln, the value, absolute value of negative a half. Cool. Let's look at cos of 2 pi on 3. Well, 2 pi on 3, we said was just pi on 3 plus pi on 3. We said pi on 3 was 60 degrees, so 60 plus 60 is 120. So 120, we know that 120 degrees, or 2 pi on 3, let's undo that, let's change colour. This one is in the second quadrant, right? Because we know it's in the second quadrant, cosine is negative in there, and because it was 2 pi on 3, 2 pi on 3 is pi on 3. It's, in the second quadrant we have 180, or pi, minus our angle. 180 minus 2 pi on 3 is pi on 3. So it's 60 degrees, so we've got minus, again, ln, the absolute value of negative half. Alright, well, what we know is that the absolute value symbol here, if we just want to think about our intuitive answer, is just half. So I have ln of half minus ln of half, which simplifies to a half outside of 0. So our final answer here is 0. And that may seem a lot of working just to get to 0. And it feels like it is a lot of working. But one thing I want to take care and focus on here is that we dealt a lot with exact ratios. And it's not going to actually be surprising that most of the time that we wanted you to do any kind of calculus with trigonometry, which includes integrating as well, we're probably going to, more often than not, use exact ratios because we're not worried, well, not worried is not the right word, we're not too concerned about the trigonometry part. We want you to be able to process these functions. In the real world, you're going to get all kinds of ugly answers, but here we want to test your ability and see your understanding of how these things work. So we're giving you familiar numbers so that you're not so caught up in trying to figure out what this random value of, cos of 7 pi on 19, for argument's sake, 7 pi on 19, some weird number, which is going to be a really weird answer in our calculator. We're going to give you nice numbers that you know the values of, so we can spend more time focusing on show us the understanding of what's happening with the mathematics and in terms of integrating or differentiating, rather than getting you to go, okay, do all this stuff with integrating, differentiating. Now tell me some really weird angle that you've also got to add some extra thought process to. Right. I hope that one was okay. For having a look at example 4 here, it's in the form of sines and cosines straight away, something that we like. In class, one of the first things people wanted to do was to cross out sines and cosines from numerator and denominator. And we know we can't do that. It's because we've got negatives and positives lying in the way here. So we know before we want to before we want to simplify our fractions, if we've got positives and negatives floating around, we want to factorize. So in class, the first instinct was people do was to factorize the numerator, and then hopefully we're trying to say that the numerator then just cancels out the denominator and we just get 1 and it's nice and easy. However, if we factorize a negative sign out of the numerator, we get negative sine of x plus cos of x all over sine of x plus cos of x dx. And when we look at that, we notice that the numerator and the denominator, they're not going to cancel each other out here. So we've got to then go, okay, well, what else do we have? And if we recall a little bit earlier, what we do have is this idea, that if I have something in the form of f dash of x over f of x, the integral of that is just ln, the absolute value of f of x, plus our random constant. So one of the things that we want to try and recognize here is that our integral is in the form of a fraction. The numerator has variables in it. And because it has variables in it, that's when we've got to start looking for this trick here and looking for this scenario here. So having a look at that, if I think about the denominator, the derivative of sine is cosine. So the derivative of sine by itself is cosine. It's there in the numerator. The derivative of cosine, we said, was negative sine. So it's there in the numerator straight away as well. So what we can go on is actually factorizing out this negative has really helped clearly identify that the derivative of the denominator is sitting there in the numerator. And just quickly as well, unlike the last question, because these are just x, the derivative just stays then as cos of x and negative sine of x. So what we're going to do here, I'm going to say that, well, this is then equal to, I'm going to factor that negative outside. So the negative 0 outside of pi, the integral of pi on 2 of negative sine on x plus cos on x all over sine of x plus cos of x dx. And I know because that's in that form there on the left, we can say it is negative ln, the absolute value of sine of x plus cos of x, evaluated between pi over 2 and 0, and just remembering that pi over 2 is 90 degrees. Now, remember what we said earlier, those nice numbers that we talked about, those exact things that we know exact values of, so we can start going through. At 0 and 90 degrees, whatever way works for you in the unit circle, we know values of sine and cosine straight away, that there's 0 and 1 depending on what we're looking for. So I know, just quickly going through now, it is just negative ln, the absolute value of at 90 degrees, sine has got the value of 1, so at sine of 90 I've got 1 plus, and cosine at 90 is 0, so it's 1 plus 0 minus, and maybe you're starting to see what's happening here. At 0 sine of 0 is 0. So I've got 0 plus 1. Whoops. It is ln, the absolute value of 0 plus 1, which just equals negative outside of ln of 1 minus ln of 1. And look, there's 1,000 ways you can think about this now, because ln of 1 by itself is just 0. So 0 minus 0. Our final answer here is going to become 0. ln of 1 is 0, or ln of 1 minus ln of 1. We're taking away the exact same values, so we would have got us to 0 again. Anyway, and surprise, surprise, we've got a nice answer out of some exact ratios dealing with trigonometry. And the key thing here was recognizing we've got a fraction and that the numerator is the derivative of the denominator. So that's a skill we're going to need to start to employ and look for on a regular basis. This is a typical question. If we just skip to the end of this question and you're asked to integrate that, that looks ugly, it looks messy, it has tan in there. We know tan sine over cos, that brings on its own world of trouble there. It's got a sec squared in there, it's got e in there, it doesn't look nice. So one skill that you'll be assessed on, and questions that help you with things when they're not in nice form, is we give you this at the beginning and we ask you to differentiate that. And what we're hoping that you guys do is when you differentiate this, it's going to look very similar, if not identical to that straight away. Identical to this. And because it's going to look identical to this, remember that integration between, so finding the area or evaluating, it's going back to that fundamental theorem of calculus, is that I've got a and b of some function. It is equal to the primitive, capital F, evaluated at b minus the primitive evaluated at a. And that if we were to differentiate this and it looks something very similar to this, well, then we can say that that is going to be very close to our primitive. And remember, our primitives, they just differ by a constant. Our families of primitives for any function will differ by a constant, and we know that that constant, when we do that, this fundamental theorem of calculus, that c ends up cancelling itself out because of that negative situation. So let's go through and find the derivative. So dy on dx is equal to, well, we love e to the tan of x because it's its own derivative. So we know that e to the tan of x is going to be part of the derivative. However, remember that with tan, it kind of behaves like a chain rule. So it's the derivative of this multiplied by itself again. And going back to our reference sheet, the interesting thing here is that the derivative of tan of x is sec squared x. So we can go sec squared x dx. Right? And when we look at this integral now, when we've found its derivative, the derivative that we found is identical to the integral that we've been asked to evaluate. So that we know the primitive of this is in the form of e to the power of tan of x. So because we know that this and this are identical, the primitive of our integral is just e to the power of tan of x. And that's what we're going to use now to evaluate. We know what the primitive is, we've just got to evaluate it at the points b and a. So we know that the integral of pi on 4 and 0 of e to the tan of x sec squared x is equal to e to the power of tan of x evaluated between 0 and pi on 4. Cool. Well, what do we know about pi on 4? Pi on 4 equals 45 degrees. And what do I know about tan of 45? Tan of 45 is 1. And what do I know about tan of 0? Tan of 0 is 0. So what we have here is e to the power of 1, because tan of pi on 4 is 1, minus e to the power of 0, because tan of 0 is 0. Well, not degree, 0. So that is just e minus 1. That's our result. Alright, looking at this last example here, one thing that we noticed, we've got sine, we've got cosine again, but we've got this annoying squared factor about it. But the cool thing is, sine squared plus cos squared, fingers crossed, by now that starts screaming out to you the Pythagorean identity, and that sine squared theta plus cos squared theta was equal to 1. Hopefully that jumped out at you. If it didn't, we've got to be looking for our trig identity sneaking in here. So we know that this integral evaluated between pi and 2 and 0 of cos squared, we know that the integral evaluated between 0, we know that the integral evaluated between pi and 2 and 0 of sine squared plus cos squared is just the integral between 0 and pi on 2 of 1, because sine squared plus cos squared is 1, which is just x between 0 and pi on 2. Well, don't need to put those in there, stop making silly things. And pi on 2 minus 0, so we're just going to be left with pi on 2 minus 0, so our final value here is just pi over 2. Alright, I hope that helps explain those examples. Good luck with doing those questions that were on OneNote and Canvas for you to complete.